Welcome back to the third part of parameterized algorithms. Here we are going to be applying iterative compression to another problem, namely feedback vertex set. Now this is also a subset problem in the context of graphs, just like vertex cover is, but unlike vertex cover, we are not trying to intercept all edges. Instead, we are trying to intercept all cycles. So in other words, what happens when you remove a feedback vertex set from a graph is that you're left with something that looks like a forest, right? So let's write down the problem definition so we are on the same page. Alright, so there we have it. That's the official definition of the feedback vertex set problem. Of course, you might recognize this as being essentially an optimization question. We are basically interested in finding a feedback vertex set of the smallest possible size, and this is the decision version of that question. And the reason I've written it in this language is because that's convenient to specify the standard parameter, which would be the solution size. So we are going to be looking at feedback vertex set parameterized by k, which is the number of vertices that we can have in our solution. That's our budget, right? So the notation here is maybe a little bit informal, so let me just go over it to make sure that we are on the same page. So when I talk about G minus S, that's basically the graph G, but with all the vertices of S deleted from it. So that's G minus S. And just to be sure about what I mean by a cycle, that's any sequence of vertices so that all the consecutive pairs have an edge between them and the sequence ends where it begins. So this, for instance, is one example, V1, V2, V3, V4 here, and back to V1. This forms a cycle. And if this cycle was a cycle in your graph, then a feedback vertex set would have to choose at least one of these vertices, V1, V2, V3, or V4, possibly more depending on the rest of the graph and what that structure is like. But basically you cannot avoid all of these four vertices because that would mean that you still have a cycle left after the FVS is removed, right? So we have to make sure to pick at least one vertex from the vertex set of every cycle that we see in the graph, and hopefully we can do this cleverly in a way that one vertex knocks out many cycles and things like that. But in terms of the definition, just notice that these two things here, of course, are equivalent. A subset of vertices S that intersects every cycle is exactly a subset S whose removal makes the graph a forest. And this is simply because a forest is an acyclic graph, right? So these are just two ways of saying the same thing, right? Maybe let's just look at one example of a graph with potentially many cycles and look at an example of what an FVS might look like. Notice that if your graph itself is already a forest, if the input graph is a forest, then the FVS is an empty set because there's no work to be done at all, right? And if your input graph is a complete graph, then you'd have to pick almost all the vertices. So for example, if you did not pick as many as n minus 2 many vertices, you would still be left with a triangle because in a complete graph, every pair of vertices is connected. So the largest that FVS can be is basically the entire vertex set almost, right? And the smallest it can be is the empty set. So the value of the optimal feedback vertex set of a graph ranges between 0 and n minus 2 if you have simple graphs. But if you have multi-graphs where you can have double edges between vertices, then the FES can be as large as even n-1. And if you allow self loops, you go further and you say that you're allowing a vertex to be connected to itself, which would be a cycle of length 1 even. Then if you give every vertex a self loop, a feedback vertex set would just have to delete all the vertices in a graph. It would have no choice whatsoever. So those are some of the extreme sort of scenarios. But let's look at this graph here. So one example of a FES would be, for example, these 3 vertices. This would certainly knock out all the cycles. Let's look at what we would be left with. So we would be left with sort of a matching here, a collection of disjoint edges in this portion. And then here we would be left with something that looks like a star. So that's a valid FES. It has 3 vertices. But now we can ask ourselves if we can do better. Is there a smaller FES? Maybe this is a good place to pause and confirm for yourself if you can find a FES of size 2 or not. Notice that you do need 2 vertices in any FES, simply because we do have 2 vertex disjoint cycles. So here, for example, we have one triangle and here is another one. And these 2 triangles don't share any vertices in common. So any FES would have to make room for at least 2 vertices, because you're going to pick at least one from here and one from here. And those 2 vertices cannot be the same because these cycles are disjoint. So the collection of any set of disjoint cycles, vertex disjoint cycles, the size of such a collection would be a lower bound on the size of a FES. This is just like we say for vertex cover, that if you had a collection of, let's say, some P disjoint edges, then any vertex cover must have size at least P. Here the analogous statement is that, if you have a collection of Q vertex disjoint cycles, then the size of any FES must be at least Q. So hopefully that's clear. So in this case, you have to pick at least 2 vertices. But the question is, can you get away with picking exactly 2 vertices? So we've seen one solution that picks 3, but let's see if we can instead just pick 2. So this one seems like a sensible choice because that knocks out all those triangles there. And then we could try to pick this vertex here. That's going to kill these 2 cycles simultaneously. And then let's look at the edges that survive. As before, we have the matching thing going on here. And now here we have one path on 3 vertices, and then we have a disjoint edge. So when we delete these 2 vertices, we are again left with a collection of, in this case, edges and paths. This is very much a forest. So we do have a FES of size 2 in this example. And as we just discussed, that's indeed the best that we can hope for. Now, in terms of FPT algorithms for feedback vertex set, it might be tempting to think about a branching based solution. So for vertex cover, we said the thing that we are trying to intercept is an edge. So we pick an edge and we branch on it. This gave us a 2 to the k kind of running time. And here we could say, well, let's pick a cycle in the graph. This we can always do using, for example, BFS or whatever. So you can try to find a cycle in the graph and then say that, well, let's branch on, all the vertices of the cycle, because we do know that at least one of these vertices must be chosen by any FES. And that's a perfectly valid branching strategy. It would be correct in terms of exhaustiveness. However, notice that it's going to be hard to bound the running time of this kind of a recursion tree, because while previously we were branching on an edge, so we always had 2 parallel universes that we created at any step. So our branching algorithm had a recursion tree which only branched 2 ways at any point of time. So we knew that if you have gone k steps deep into the recursion, you have generated something like 2 to the k vertices, right, in the branching tree. But here, we really have no control over how many parallel universes we are going to create. That is going to be a function of the length of the cycle that we choose to work with. Now, we could say that we go and look for a shortest cycle, because that would kind of lead to fewer branches. So the shorter the cycle, the fewer the branches. But it's conceivable that you have a graph where the shortest cycle is quite long. In particular, it's not bounded by k. So if you are creating, let's say, a function of n many recursive calls, then that's not a good place to be. Now, I'm making this comment only in very general terms. That is not to say that this cannot work. In fact, with some effort and the right combination of ideas, you can actually come up with a branching-based algorithm for FVS, which turns out to be FPT. And in fact, the number of branches actually does look like a function of n, but somehow in the end, the analysis works out magically to be FPT. And the idea is to see if we can do some pre-processing to ensure that a short cycle is always available to us to branch on. So it's an interesting thought, and I will leave it to your imagination to try and figure out what this branching algorithm could look like. And of course, there are pointers in the notes where you can go and look it up if you are curious. But the focus of this discussion here is not to design a branching algorithm for FVS, although we will end up branching a little bit eventually. But the idea is to see how we can use the iterative compression framework to come up with nice algorithms for FVS. So the overall framework of the iterative compression algorithm is going to be exactly the same as what we had for Vertex cover. So I will not set it up again, but I will only focus on solving the compression version of the problem, because we already know that once we know how to compress solutions that are given to us, we can actually solve the entire problem. So here is FVS compression, which is exactly like FVS, with the difference that we have also been given a bit of a head start. We have access to a solution of size k plus 1, and the question is, can we make good use of this to come up with a solution of size at most k? Now, notice that the iteration works exactly the same as before. You can isolate your favorite k plus 2 vertices and pick any k plus 1 of them to see that you have a feedback vertex set of size k plus 1 to begin with. You could have gotten away with perhaps picking k plus 3 vertices and picking some k plus 1 vertices in your solution. So let's say you start with some k plus 3 vertices in the graph and you pick any k plus 1 sized subset here. What you would be left with at best is an edge, and you can form a cycle with an edge. So this would typically work if you were working with simple graphs, but as we will see, we might be making modifications to our graph in a way that requires us to allow for double edges or multiple edges between vertices. So we are not going to assume that our graphs are simple, even though you can assume perhaps that the input graph is simple. That's not something that we will be able to maintain as an invariant. So as we go along, our graph may evolve to becoming a multigraph, right? So the safer thing to do is to say that we will start with, or in general, we're going to start off with k plus 2 vertices, and we are going to pick a k plus 1 sized subset, and we will only be left with a single vertex. Now, you might say, well, what if this vertex is a self-loop? But in general, we're going to assume that vertices don't have self-loops, because if for some reason, even if you do create a self-loop as a part of your procedures, the moment you see a vertex with a self-loop, you can just pick it in your solution because you don't have a choice. So that is a polynomial times sort of a pre-processing step that you can always apply, even recursively. Whenever you see a vertex with a self-loop for feedback vertex set, just choose it in your solution and move on, adjust your budget and move on. So it's safe to assume that we don't have vertices with self-loops on them, But if you have a double edge, then that's a little bit like vertex cover. We don't know which one of these endpoints of that double edge must go into the FVS. We know that at least one of them is in the FVS, but we don't necessarily know which one. So we cannot just wish it away by forcing something. We would have to let them be and then let the algorithm take care of things in due course. Anyway, all this is to say that iteration works almost exactly as it did for vertex cover. So if we can solve the compression problem, if we can figure out whether a given solution can be compressed or not, then the overall algorithm will basically work as advertised. It's going to take time, that's basically the time for the compression routine, with a polynomial overhead to account for the iteration, exactly as before. So we will not repeat the whole algorithm, but instead we will just focus on the compression routine. So let's take a closer look at what's happening with the compression part of iterative compression. So we have here our input solution T, and this is a FVS this time, and let's remember that T has k plus 1 vertices, and we know that what's outside here is a forest, that's V minus T, so its connected components are basically trees. Remember that when we were working with vertex cover earlier, we had an independent set sitting outside, but now probably have all kinds of different structures. All we know is that there are no cycles. So that's what's going on out here. And the question is, can we use this structure that we can visibly see to determine if there is a smaller FVS or not? And in fact, just like we did for vertex cover, we're going to start off by guessing the intersection of the FVS that we are looking for, which I will continue to call S. So let's say we're looking for S size at most K, which is a feedback vertex set. I might have said vertex cover a minute ago. So what I'm really looking for is a feedback vertex set. So a feedback vertex set of size at most K. I'm going to continue denoting that by S. And we're going to try and guess S intersection T. And of course, what's going to be left is automatically T minus S, right? So these are the vertices that we are saying we won't pick in our optimal FVS, in the FVS that we are looking for. And these are the vertices we say, oh, we were right about these guys, let's keep them in our FVS. So T actually made choices coinciding with S in this portion, and choices that don't agree with S in this portion. So just as before, we guess all possible ways in which this can happen, because of course the algorithm doesn't know what S is, it doesn't know what S intersection T is, but given that T is small, we can guess S intersection T by simply going over all subsets of T, right? So that's essentially this giant outer for loop, which is going to already take up 2 to the k iterations. And now the question is, what do we do within a guess? In other words, what we are thinking about now is, having fixed a particular guess, what should our next step be? And if we zoom into the issue here, basically we want to know, how can we do the work that the vertices in T minus S were doing before for us, using hopefully fewer vertices than we used in T minus S. It may be useful to recall how we handled this for vertex cover. So for vertex cover, our first observation was that if there are vertices within T minus S that already have an edge, then there is no hope for this particular guess, because we are saying that we want a vertex cover that covers all the edges, but here is an edge, both of whose endpoints we have expressly forbidden from being picked. So we said, well, this is a bad situation, so we can simply move on to the next guess. But if this was not the case and the vertices in T minus S did induce an independent set, then the next thing that we said is, well, let's look at what are the edges that these vertices are covering. And it makes sense to say that, well, now we need to look at the other endpoints of all of these edges, and in particular, we need to focus on the endpoints of these edges which are in V minus T, and we go and pick them up and check if the number of things that we picked up was less than the size of t minus s. If it was, then we are in business. We have found a smaller vertex cover, and we can actually stop here. Otherwise, we move on to the next guess, knowing that the replacement here was too expensive. So very briefly, that was a recap for what we did when we were discussing iterative compression for vertex cover, specifically the compression problem. If you are here not having seen the previous discussion on vertex cover, then this may not have made a lot of sense, and I would recommend going over that first before doing the feedback vertex set algorithm. Okay, all right. So here, what is the first analogy to there being an edge in t minus s? Remember, what we are basically saying is that there is a forbidden thing that we are trying to intercept, but we are not allowed to intercept it. So for vertex cover, it was that there is an edge sitting inside t minus s. For feedback vertex set, the natural issue would be if there was a cycle sitting completely inside t minus s. If this was the case, then we are going to have a hard time killing this cycle using vertices outside of t minus s. There's nothing that we can pick from outside of t minus s that would actually intersect this cycle. But remember, the very definition of a feedback vertex set requires us to pick at least one vertex from each cycle. So if we see a cycle that's fully sitting inside t minus s, then just like vertex cover, we give up on this guess. We say that, look, this is not tenable. We will never be able to extend S intersection T as chosen here to a complete FES for the entire graph by only picking vertices from V minus T, because no matter what we pick, here is a cycle that's going to be completely left out. Okay, so we discard this guess and move on. So what we do know now is that the structure induced by the vertices of t minus s must be acyclic for us to have any hope of actually building on this guess. Okay, so a useful thing to do now would be to just zoom in on t minus s and v minus t. Let's just delete s intersection t, because these vertices we are going to choose in our FES anyway. So let's get rid of them. They've done their job. They've taken with them the cycles that they intersect. So we can forget about their presence for now. What we do need to remember is how many vertices did we get rid of, because that gives us our adjusted budget. Remember that we're still looking for a feedback vertex set of size at most k, and we have used up size of S intersection T, many vertices of that budget. So our remaining budget, which I'll denote by k star, is basically k minus the size of S intersection T, which is basically our current guess. So S intersection T is not something that we know, but remember we have this giant for loop which is going over all the subsets of T. So for a particular fixed subset of T, we are going to say that k star is k minus the size of that set, assuming that the set is our guess for what goes into our FES, the one that we are looking for. So strictly speaking, the notation S intersection T is really somewhat meaningless because we don't know what S is. Of course, T is given, but S intersection T is my lazy way of expressing that we are considering the current guess. So if you want to be a little more specific about this, essentially what we are doing is the following. So we're saying for X subset of T, and again, we're only going over strict subsets because taking all of T would be too expensive. So for all proper subsets of T, what we are saying is, well, let's imagine for now that the FES that we are looking for overlapped with T exactly at the vertices of X, right? So when we fix such a choice X, what we are saying is, well, K star, our remaining budget is K minus the size of X. That's what's going on here. And then we are going to proceed from here. And that's what we want to talk about next. Now, like I said, it's convenient to just forget about S intersection T, which for a fixed guess X is basically, well, what we want to focus on is T minus X. X is what I want to forget about, because like I said, our semantics is that X is our guess for the things that T was correct about. T intersection S is what we are imagining X as, right? So let's basically remove the vertices of X from our graph. So let's focus on this graph H defined as G minus X. And in H, we have basically two things. We have V minus T and we have T minus X. These are the two things that constitute the vertex set of the graph H, right? And what's special about both of these paths, as we've just discussed, both of these paths must induce forests because, well, V minus T induces a forest because T was a FVS to begin with. That's what was given to us. And T minus X induces a forest because if not, then we can just move on from this guess. So that's basically a sanity check. So we say if T minus X contains a cycle, then move on to the next guess, break out of this loop and break out of this iteration of the loop and move on to the next guess, because there's absolutely no way that we can kill this cycle given that we are forbidden from picking anything from that cycle. So we are forbidden because that's our current guess, right? We have said that we don't pick anything outside of X from T. Okay, so under the circumstances, we know that if we pass our sanity checks and this guess looks promising, then V minus T and T minus X are both forests. And it's worth remembering that T minus X in particular is a small forest. It's a forest on a small number of vertices. Because it's a subset of T and T had K minus 1 vertices to begin with, we know that the size of T minus X is also at most K minus 1. So that means that we can perhaps take advantage of this in some way, and in fact we will do that, as we will see. But for now, let me clean up this picture a little bit so as to, like I said, forget about X, because we might as well delete the vertices of X from our graph. So what are we left with? So we are left with, on the one hand, T minus X. So this is the forbidden forest in some sense. We are not allowed to pick anything from here, but we know that it is a forest and it is small. So the size of T minus X is at most K plus 1. And we know that this is the set of vertices that, as per our guess, is not going into the solution. So we are not allowed to pick up anything from here. And we are also left with this larger forest, which was the original forest from the feedback vertex set given to us as input. And so this would typically have n minus K plus 1 many vertices. So size of V minus T is n minus K plus 1. So this is the larger forest, but this is the forest from which we are allowed to pick vertices to get to our final feedback vertex set. Remember that we are working with a current budget of K star, which is K minus the size of X. And that's the budget within which we have to kill all the cycles that we see in this picture. So essentially we have a graph which is partitioned into two forests. One of those forests is small, and we are asking ourselves, can we pick at most K star many vertices from the large set, from the large forest, so that we kill all the cycles. So now you might be wondering, where are these cycles though? Because all we see is two forests. However, notice that there are edges that connect these forests with each other, edges that go across V minus T and T minus X. So all the cycles that you see would typically be of this form, involving edges that go across like that. So notice that this would involve a cycle which looks like that, right? So these are the cycles that we are trying to kill, but we can only do that by picking vertices from V minus T, right? So that's our situation. Now, before we get to resolving this completely, let's make a few easy observations, which is going to make life simpler for us as we go along. So First of all, what if we have a cycle which has only one vertex from v minus t? Okay, so here's a simplistic scenario. Here's a cycle which passes through exactly one vertex from v minus t, and the rest of it is sitting in t minus x. Okay, now if we see a cycle of this sort, then we can actually force the vertex in v minus t, this guy here, into our solution. And the reason for that is we know that we have to intersect the cycle with our FVS, but the cycle has only one candidate vertex which can belong to our solution. We don't really have much of a choice here. So when we see a vertex like this, we're basically going to make a record of this by updating our graph and updating our budget. And if we are keeping track of the FVS that we are building, let's say we are tracking that with S. So to begin with, S would have been initialized to X, for example. And when we see a vertex like V, as in this picture, then what we are going to do is say, well, let's update S to include the vertex V. Let's adjust our budget and reduce it by 1, our remaining budget, because we have now used up one vertex we've added one vertex to the solution, so our remaining budget reduces by 1. And just as we got rid of X, we can also delete the vertex V from our graph. So we can update the graph H to be the graph H now without the vertex V. So we can do this anytime that we see a vertex V that is in v minus t and that participates in a cycle where all the remaining vertices of the cycle are in t minus x. And one way to detect this is to say that, well, look at a vertex V and check if it has two neighbors in the same tree of t minus x. So whenever a vertex V has two neighbors in a common connected component of t minus x, then you know that in that component there's going to be a path from, so let's say these neighbors were x and y. So there's a path from x to y completely in t minus x, and v is adjacent to both x and y. So that path between x and y combined with v gives you a cycle in which the only vertex from v minus t is this vertex v out here. Okay, so that would basically force v. So every time you see a vertex v that has two neighbors in the same component of t minus x, we know that we can make progress, reduce our budget, and simplify the graph further. Okay, so from here on out, I'm going to assume that every vertex v in v minus t only has neighbors in different connected components of t minus x. Now, the next thing that I want to talk about is the concept of short-circuiting a degree 2 vertex. So for feedback vertex set, short-circuiting is a very common simplification or pre-processing technique. So let me talk about short-circuiting in general terms first. Suppose you have a vertex in your graph that has degree exactly 2. So let me call this vertex U. And let's say its neighbors are V and W. Notice that any cycle that passes through the vertex U must come through V and exit through W, or the other way around. So of course we are not looking at a directed graph, so this directionality is simply an intuitive way of talking about cycles. So let's say you are following a cycle along its trajectory, you know that the cycle contains U. Notice that the cycle must also contain the vertices V and W, because those are in some sense the gatekeepers for the vertex U. You cannot enter the vertex U without going through its two neighbors. It's a degree 2 vertex, so these are your only options pretty much, right? So any cycle that passes through U must necessarily also involve its two neighbors, because a cycle itself can be thought of as a two regular subgraph of the graph. And if there's a vertex which only has two neighbors, then both of its neighbors must also belong to the cycle. We don't have a choice. So all of this is to say that if somebody gives you an optimal feedback vertex set that contains the vertex u, then you can transform this feedback vertex set into another one that does not contain the vertex u, but instead contains, for example, the vertex v. That would also work. Keep the rest of the keep the rest of the feedback vertex set exactly the same, but shift from u to v or from u to w. These choices will work just as well as u, because every cycle that u intersects, v or w would also intersect all of those cycles, right? So this would be a general observation. The way to leverage this observation as a concrete simplification rule is to say that you can shift from the original graph to a graph where you've gotten rid of the vertex u, but instead you add an edge between v and w. And the reason you add this edge is to basically remember all the pathways that went through u. If you simply deleted the vertex u and did nothing, then you're definitely changing the structure of the graph and you're forgetting about some cycles, and those instances would not be equivalent. If you disregard the vertex u, you drop it, and you reduce the budget in an overeager fashion, saying that, well, we are going to, if in your imagination you're thinking that we will pick the vertex u, that may also not be correct, because possibly you don't need to indulge in the vertex u at all for a FVS. So the point here is to not touch the budget at all and not make any commitments towards picking vertices in the FVS. Instead, all we are saying is that we will preserve the structure of all the cycles by simply remembering the presence of the vertex u via its neighbors, via an edge between its neighbors. And this is where we may lose the invariant that the graph is simple. So it's possible that we had a simple graph as input, but now even if there was an edge between v and w before, we are going to add an extra edge on top of that to remember the presence of the vertex u. Okay, so we at this point, when we apply this kind of simplification, we do end up creating a multigraph, but that's something that we can live with. It's worth it in the sense that once you have simplify the graph according to this kind of degree 2 simplification or short circuiting, you do end up in a situation where you can say that the graph has minimum degree 3. Of course, if you are careful, you might wonder, how can we say minimum degree 3? What about the degree 1 vertices? And that brings me to the degree 1 rule, which we can always apply for feedback vertex sets. So the degree 1 simplification is simply that if you have a vertex that's degree 1, right, then simply remove it from the graph and nothing changes. So you can go from g comma k, an instance of FVS, to g minus v comma k if v is a degree 1 vertex. And the reason this works is because degree 1 vertices never participate in cycles. So it's like saying that if you have a vertex cover instance, then you can throw away isolated vertices because they never really make a difference to the problem, right? So you can throw away isolated vertices and not change the budget. For feedback vertex set, you can throw away isolated vertices and vertices of degree 1. So in fact, you can delete all vertices that have degree at most 1, because a degree 1 vertex never participates in a cycle and therefore is of no interest to any optimal FVS. So we might as well not have these vertices around. It does not change the cycle structure of the graph in any way. The budget can stay the same because these are really not vertices that we were going to pick at all. So this is the low degree simplifications that are pretty standard for for feedback vertex set. So when we are done with these simplifications, we usually end up with a graph where the minimum degree is at least 3, and that turns out to be useful. However, remember that we are not working with just feedback vertex set. We are working with feedback vertex set with annotations, right? So by annotations, I mean we have these vertices which have been marked as forbidden, as vertices that we cannot choose to be in our solution. So now we do have to be careful. So for instance, what if both V and W were vertices in T minus X, for instance, right? Then this is not a safe simplification because, for instance, if they already had an edge between them and then we get rid of U this way and replace it with an edge like that, then we are creating a cycle of length 2 which basically cannot be destroyed. But in the original graph, we could have handled this by picking the degree 2 vertex U, right? So we do have to be careful about what happens when both our neighbors of a degree 2 vertex are in T minus X. Then this simplification may not go through as is, but we can still do some amount of short circuiting. And I claim that if you have a degree 2 vertex where at least one of the neighbors is in the safe zone, is in V minus T, then we can still do this simplification where we get rid of the degree 2 vertex and instead to remember what the degree 2 vertex brought to the table, we add an edge between its two neighbors, as is usual with the standard short circuiting, right? So we simplify our degree 2 vertices in this sort of limited addition fashion, right? So if you see a degree 2 vertex, any degree 2 vertex in V minus T in particular, let's only focus on degree 2 vertices in V minus T because it turns out that those are the only ones that really matter as we go along. When we look at a degree 2 vertex in V minus T, if it has at least one of its neighbors in V minus T again, then we are going to do the standard short circuiting where we say delete the degree 2 vertex from the graph and add an edge between its two neighbors. Even if its two neighbors already had an edge between them, add an extra one to remember the vertex that we just got rid of. Okay, so this is the limited addition degree 2 simplification. And if you go over the proof of why the original degree 2 simplification works, you can very easily adapt it to work in this setting as well. The intuition is basically to say that suppose you had a feedback vertex set of size at most k star that chose vertices only from V minus T, and suppose such a FVS chose this degree 2 vertex here, right? If it contained V, well, I can give you a feedback vertex set that does not pick V. It does the exact same job as the one that you have with the exact same number of vertices. And I'm going to do that by shifting from V to one of its neighbors, which we know that there's at least one neighbor in V minus T. So there's at least one of them that we can pick to do the work of V. And of course, it's possible that this neighbor was already chosen, in which case you can actually just drop V from your FVS and it would still be a FVS. Okay, so because it would be redundant to pick a degree 2 vertex along with one of its neighbors, because then the neighbor is already doing all the work that the degree 2 vertex can do. So typically in a minimal or an optimal FVS, when you have V, you would not have its two neighbors. But the point here is that you can always swap V out with one of its neighbors. And you can do that provided the neighbors are not forbidden, which is why we're saying that we apply the degree 2 simplification only when we are sure that at least one of the neighbors of the degree 2 vertex in question is in V minus T. And if there is one, then we proceed. So let me write this down explicitly here. So if the degree of a vertex in the entire graph, the current graph under consideration is H. So if the degree of a vertex is 2 and the neighborhood of this vertex intersection V minus T is non-empty, which means it has at least one neighbor in V minus T, then we basically say, okay, let's move on to this instance where we remove this vertex V from H, but we add the edge PQ, where I'm using PQ to denote the two neighbors of V. So we remove the vertex V and we add this edge, and the budget remains unchanged. So it's still K star. Okay, so this is one simplification. And we also do the degree 1 simplification. So if the degree of any vertex in H is at most 1, then we simply remove such a vertex and keep the budget unchanged. So those are all the simplifications that we are going to execute. And now let's think about what we have achieved with all this. What is the structure of the graph when it's simplified with respect to all of these simple rules that we came up with? Just to quickly recap, what we said is that if you have a vertex in V minus t, which sees at least 2 vertices in the same tree of t minus x, then we force that in our solution. If we see a vertex whose degree is at most 1, we simply delete it without changing the budget. And if we see a degree 2 vertex in V minus t, at least one of whose neighbors is again in V minus t, then we short circuit it. These are the 3 things that we said we will do. Having done all this, let's go back and look at this picture. So recall that this is our small forest, large forest situation, where we are looking for a subset of at most k star vertices from the large forest, which can hopefully intersect all the cycles that go across, and we are now trying to find this subset. Now what I want to do is to begin with focus on one of the trees in V minus t and zoom in to a leaf vertex in this tree. Notice that every tree has at least one leaf, so we are going to start our story from such a leaf vertex. And because it's a leaf in a tree of V minus t, it has one neighbor in V minus t. And of course, this is not the only neighbor that it has in this whole graph, because if it was indeed the only neighbor that it had in this whole graph, or maybe if this was a tree with just one vertex, which means it doesn't have any neighbors in V minus t, in both of these scenarios, the degree at most 1 pre-processing or simplification would have actually deleted this vertex. So we know that the vertex that we are currently focusing on, let me again call it V, this vertex must have at least one other neighbor to have survived the degree at most 1 rule. Now where can this neighbor be? Well, it can't be in V minus t because it's by definition a leaf in a tree of V minus t. So the other neighbor must necessarily be in t minus x. So let's say V has a neighbor u in t minus x. Can this be V's only other neighbor in the graph? Well, if this was the case, then V would have been a degree 2 vertex with at least one neighbor in V minus t, so it would have been short-circuited out of this picture. So U cannot be V's exclusive neighbor in t minus x. There has to be at least one more. Now, this extra neighbor that we know V must have, can it be in the same tree that U belongs to? Well, the answer to that is also no, because if we had another neighbor in the same tree that U belonged to, then this would have also been subject to one of our simplification rules. So here we know that we have a cycle where V is the only vertex from V minus t on this cycle. So we would have deleted V and reduced the budget if this was the picture. So we do know that V has an extra neighbor in t minus x, but that extra neighbor is in a different tree of t minus x. So these are all the things that we know must be true from all the simplification that we have done so far. Now, having set up this picture, we are now ready to describe the heart of the compression algorithm, which is going to be a branching algorithm. And it's actually a very simple branching algorithm. What we are going to say is explore the 2 natural possibilities, which is that we pick V in our solution and we don't pick V in our solution, right? Now, what happens when we pick V in our solution? Well, the natural thing that happens when we do that is our budget K star reduces by 1, and of course we end up also deleting V from the graph and so on. So that's nice. There's something that's dropping, and we know that that's good for branching algorithms. So K star is small. It's bounded by our parameter, and if that's reducing, that's wonderful news. What happens when V does not belong to the FVS that we're looking for? That's the other branch. And here K star actually does not drop because we have decided to not pick V, right? But notice that if we decide to not pick V, we have this region of our instance which is basically collecting forbidden vertices, right? So it's the set of vertices that we have committed to not picking in our FVS. And because we have decided in this branch that V does not belong to the solution that we are looking for, we can have V join this club, right? So what we can do here is basically say that update T minus X to include the vertex V, and update V minus T to drop the vertex V. So basically V changes locations, nothing changes in the graph in terms of deletions, nothing changes in the budget, but in some sense we now have a different perspective on where V is located. So in this branch what we are going to do is basically push V upstairs. But what good does that achieve, right? In terms of something measurable that drops so that we can control the depth of the branching, what do we have? Well, a key observation here is that because the vertex V has this property that it has at least two neighbors in two different trees of T minus X, when V joins T minus X, it's going to merge two components in T minus X. So the number of connected components of T minus X drops by 1. And notice that T minus X to begin with was a subset of at most K plus 1 vertices. So it had at most K plus 1 connected components to begin with, and every time we push a vertex of the sort that we are branching on, every time we push such a vertex into T minus X, the number of components that it has basically drops by 1. Okay, so this is a very interesting sort of a branching algorithm because we have an unusual measure. So let's consider the measure defined by, so let's say we're looking at the instance H. Let's define the measure as the budget plus the number of connected components in T minus X. We know that overall this measure to begin with is bounded by 2 times K plus 1, because we know that K star, our remaining budget, is at most K, and we also know that the number of connected components in T minus X is at most K plus 1. So in fact it's this is bounded by 2K plus 1, not 2 times K plus 1, but 2K plus 1. Right, so that's an upper bound on the measure to begin with, and what we know is that this measure is reducing by 1 in both of our branches. Right, when we pick V in the solution, the measure reduces because K star reduces by 1, and when we don't pick V in our solution, the measure reduces because well, at this point the number of connected components of T minus X reduces by 1. Right? So we know that our branching algorithm cannot go more than 2K plus 1 levels deep because one of these things is reducing all the time. Right? Might be a good exercise to think about what happens when all the connected components in T minus X have merged into one giant component. Right? Does that emerge as some sort of a base case? Just think about what happens when that component of the measure basically hits 1, because at some point you can't keep merging components forever. There were at most K plus 1 to begin with, so at some sort of depth and some recursive instance, you'll see that all the components have merged. It's a nice exercise to think about what happens in that scenario. And of course, at some point, you're also going to run out of your budget when that happens. And if there are still cycles left in the graph, then you know that that's a standard sort of a base case where you say no. So I leave it as a fun exercise to develop some intuition for what's going on at the base cases, but hopefully you can see that we have a way of controlling or analyzing how deep this recursion tree goes. Okay, so there was a quantity that we defined associated with every instance, and the instance that we start out with, which is basically g minus x. So remember, we said we have a guess for where our optimal FVS intersects the given FVS t. And that guess we called x, and we said, well, let's look at the graph h defined as g minus x. So we're working with a fixed guess at the moment, and so our graph is g minus x. In g minus x, we applied certain simplification rules. We got rid of vertices whose degree is at most 1. We short-circuited certain kinds of degree 2 vertices, and we also forced vertices in the solution if they were the only vertex that participated in a cycle that was eligible for destroying that cycle. So we did all of that, and then in the graph that remained, in the instance that remained, with whatever budget remained, we started our branching process. And in that initial graph, this measure, which we said is the current budget, whatever that is, and the total number of components in t minus x, whatever that is, the sum of these two things does not exceed 2k plus 1. So that's the value of the measure in the instance that we start with. And now we carry on with our branching, and we know that in both branches, this measure drops by at least 1. So it might drop by more if we are lucky. For example, it's possible that V is adjacent to a lot of different components. So it's possible that the measure drops more dramatically in the branch where we don't pick V in our solution. But for the sake of analysis, which is in the worst case, we just assume that the measure drops by exactly 1 in both branches. So we know that the overall sort of running time is going to be bounded by 2 raised to the value of the measure at the beginning. And notice that this basically amounts to an order 4 raised to k algorithm, because that's 2 raised to 2k plus 1. And that's basically it. That's the entire algorithm. Notice that when the measure drops to a point where you don't have connected components to merge anymore, or you don't have a budget left, these are the base cases that emerge. And I said that I will leave it as a bit of an exercise to figure out what happens. In some sense, these are basically instances that you can deal with in polynomial time. By the way, always remember that once we do execute one layer of the branching, we've committed to picking V or not picking V. In the resulting instance, we will again apply our simplification rules just to ensure that we always have a vertex of the sort that we're looking for that will give us these breaks in both directions, right? So, of course, whenever we choose to pick a vertex in our solution, the budget is going to drop, so that's the easy branch. But we also want some leverage, some progress when we don't pick this vertex in our solution. And if we just worked with some arbitrary vertex, it's not clear that you will be able to make a dent on the number of connected components in t minus x. So by carefully choosing a leaf vertex which is guaranteed to have at least 2 neighbors and 2 different components, we actually get the drop in the measure that we are looking for in the other branch. So it's really a very clever set of ideas. When we were working through the simplification rules, you might be wondering, why are we doing all this? Although each of those rules seems like they work for sure, but where are they coming from, and why do we want to apply these rules in particular? At least hopefully in retrospect, it's clear why these rules are useful. They somehow give us exactly what we need to be able to execute this branching idea. Okay, so that's kind of the entirety of the compression algorithm. Of course, this whole thing gets plugged into this 2 raised to k sort of an outer loop, and you can actually do a more careful analysis of the running time by not saying that the outer loop where we are guessing the choice of x, we could say that, well, that loop runs 2 to the k times, and you can multiply it by 4 to the k to get a loose upper bound on the running time. But instead, if you're a little more careful and you count carefully the sizes of the subsets that you're removing, and you do a more precise analysis of the running time, you get a better bound. And in fact, you can show that this algorithm runs in time bounded by 5 raised to k asymptotically, of course with appropriate polynomial overheads. And I will leave that analysis as a fun exercise to work through, but of course you can also look it up in the notes and in the practice assignments. So I would say try to work through it once yourself, just to explore the possibility of a tighter analysis on your own, and you can always cross-check the calculation with the notes that are available. So with that, I will stop here, and this was our second example of iterative compression applied to a parameterized problem. And I think it's a really nice example because we see a lot of ideas coming together. We see simplification rules, we see a clever branching idea, branching algorithm where the branching itself is a very simple branching rule, but the measure that we use to analyze why the recursion tree is bounded is rather clever, and those ideas are intertwined with the simplifications that we carried out. So I think it's a really nice algorithm with several ideas coming together really nicely, and I hope you enjoyed this as much as I did. And that's a wrap for now. I'll see you in the next video. Thank you.